on reflections and observations. And so we've got a panel of four, starting with Gordon Hughes, who has over 40 years as a consulting engineer in general practice. He's served on the SESOC Management Committee and Engineering New Zealand Competency Assessment Board, and is a practice area assessor. He's a life member of SESOC and a fellow of Engineering New Zealand, and Gordon has a special interest in learning from mistakes. Just before you get cracking, Gordon, I'll introduce the other panellists before you get going. So we've got Stanley Chung, who's a senior structural engineer at WSP in Wellington, with 12 years experience in delivery of structural engineering solutions to a wide range of multidiscipline buildings and infrastructure projects across New Zealand. Stanley is a WSP project client manager and team leader for Wellington City Council Regulatory Review, and we heard from Stanley at the last conference, which was a fantastic presentation, so I'm really keen to hear what he's got to say 2 years on. Carl Ashby is our third panellist. Carl's got over 27 years experience and is a fellow of Engineering New Zealand and a director of building structures for WSP, also based in Wellington. He is a past president of the New Zealand Concrete Society and has served on the management committees of SESOC, NZSEE, NZCS, as well as recent NZS 3101 Concrete Standard Committee and the MBC5 Yellow Book Guidelines. And finally, we've got Tony Stewart, who is an Auckland-based structural engineer and principal at Compusoft Engineering. Tony has extensive experience in analysis, design and assessment of a broad range of structures, and is the key point of contact within New Zealand for the CSI software. So over to you, Gordon.
Thank you, Hamish. There are old pilots and bold pilots, but no old, bold pilots. That was something that I learnt when I commenced flying. In fact, I started flying before I went out on practice of my own over 40 years ago. So I've had looking today at the core elements of human factors taken from the aviation industry where they've been used successfully. I look at those to see if they are any use to us in improving structural engineering. I'm also going to have a look at some design tasking research carried out in Sweden, some studies on errors and the differences between attitude, values and the role of empathy. Has anyone here ever made a mistake? Captain Neil Downey, a pilot with Aer Lingus, asked attendees at a conference of human factors for the Royal College of Surgeons and Physicians the same question a couple of years ago. So he said, we're in the right room. In aviation, we assume we're going to make mistakes, and our whole mindset and systems based around that. I'm not sure that we can say that. Oops. If a flight crew member makes a mistake, chances are everyone's going to die with them. If we make a mistake, fair chance it might never be discovered until after a major environmental event such as a severe earthquake occurs. The research shows that almost half of the structural failures are a result of human error in design. Whoops. So losses from errors in structural engineering are significant, and an Australian study indicates that they add up to 7% extra to the cost of the project. Other research findings indicate that self-checking of designs results in 2.5 times the chances of error compared to independent checking. And then 17 Swedish engineers were given a task to design 2 projects, and the answers had a range of 300%. So as we heard this morning, and most of us are aware of, engineering mistakes continue to be in the headlines, New Zealand, Australia, and overseas. Something's wrong. And as Paul said, when quoting Einstein, I think it was, do the same thing, you get the same answer. So I think we've got to look at doing something different. In aviation, the passenger death rate was recorded from 1920 through to 1977, showing a steady increase. And after that, it's descended with a tenfold reduction. In 1977, two Boeing 747s collided on the ground at Tenerife Airport, killing 583 people. And Captain Downey, in his address, said that was a watershed moment for aviation, because we decided as an industry that we had to do things differently. Began as cockpit resource management, and then crew resource management, and then fully blown human factors. And that study of human factors and implementation of it has and continues to have a significant improvement in aviation safety. Some other industries have taken on human factors, especially those in safety critical and high risk areas, including transportation, oil and gas process industries, and the nuclear industries. The medical profession in the UK recently called on aviation experts on human factors to try and improve their performance in hospitals. Now, we as structural engineers, we study materials and systems, but little, if anything, formally about the people doing the structural engineering. Human factors, what are they? On the slide there, there's a bunch of different disciplines involved, various forms of psychology, industrial engineering, cognitive science, computer science, and medical science. So the term really refers to the range of issues affect how people perform their tasks in work and non-work environments. It involves applying knowledge about human body and mind to better understanding capabilities and limitations. They are social and personal skills which complement our technical skills. Now, for today, I've taken the 9 core headings from the New Zealand Civil Aviation syllabus on human factors, and they're just very brief introductory comments under each heading. First, threats and errors. In aviation, that's generally described as an event or error that can compromise safety. Errors can be slips or laps, skill-based errors, or carrying out an action incorrectly. A mistake is where the action's incorrect. And this type of human error can apply and happen to even the most experienced and well-trained person. And in the introductory Engineering New Zealand webinar series Lessons Learned that Glenn Curry and I prepared, we looked at that in a bit more detail. Organisational factors. The culture of an organisation is crucial. In aviation, where a just culture or no blame reporting of incidents and mistakes is encouraged. So if the proper resources are available and to hand, there's a greater chance that the task will be completed effectively, correctly and efficiently. In a happy workplace where openness, good communication, positive support will encourage higher productivity and lead to fewer errors and mistakes. Stress and fatigue. Fatigue is a general term used to describe physical and or mental weariness extends beyond normal tiredness. Often leads to mental fatigue, a decrease of attention, ability to perform complex or even quite simple tasks with customary efficiency. Stress. It's a whole bunch of types of stresses, but usually they can be accumulative. They result from long-term demands on the physiology by life demands such as family relationships, finances, illness, bereavement, divorce, or even winning the lottery. I wouldn't mind that one. Stresses and fatigue affect structural engineers, and they should be monitored and mitigated because they can lead to an increased rate of errors and mistakes. Information acquisition and processing. This involves attention and perception, so we need to have techniques for improving, enhancing our memory and development of skills, and these are especially important in both aviation and engineering. Situational awareness and workload management. Situational awareness is really just knowing what's going on around us, and traditionally applied to flight deck and the pilot knowing what was going on around him or her, so they then could anticipate and know what they might have to do next. Workload management's the process, obviously, of distributing work amongst employees and monitoring its use and making sure that people are not overloaded and they've got the right amount of work ahead so that they can perform their tasks efficiently. Again, important in both aviation and engineering. decision-making. Attention and perception shortcomings can clearly affect our decision-making. If we perceive something incorrectly, it may mean that we'll make the incorrect decision and then an inappropriate action. So we depend on our memory to make decisions. Sensory and short-term memory have limitations both in terms of capacity and duration. Important to bear in mind that our memory is fallible, so that information may not be stored or may be stored incorrectly. Communication. Poor communication is about always on the list of aviation accident reports. It refers to the transmitter, the receiver, as well as the method of transmission. Transmitted instructions may be unclear or inaccessible. The receiver may make assumptions about the meaning of these instructions, and the transmitter may assume that the message has been received and understood. With verbal communication, it's common that only 30% of a message is received and understood. So good communications are critical in both structural engineering and aviation, and poor communication often features in engineering disciplinary cases. Leadership and team behaviour. Leadership's quite difficult to define, but it's obvious when it's seen. It's the ability to harness diverse personalities to achieve an objective. And all of the human factors are required to develop individuals into a team so we can achieve outcomes greater than the sum of the parts. Cultural differences may mean that team members are unable to express concerns and or to not allow others to express theirs. Unassertive team members may be forced to go along with the majority decision, even when that's wrong, or they believe it's wrong. Automation, vigilance and monitoring. Well, John's just been talking about some aspects of this. In aviation, automation is a vital and increasingly dominant part, and vigilance is closely related to situational awareness. So workplace procedures, scanning, two-way communications, use of checklists are important to maintain vigilance. And that's really important in aviation because it's a dynamic situation. But also, with increasing and more extensive use in structural engineering, monitoring is important, as is vigilance, but even more important is the understanding of the assumptions that the automation is based on, and that together with adequate vigilance and monitoring will need to take place as more and more of the traditional engineering tasks are taken over by automation. The other group a group called the Dirty Dozen comes from aviation maintenance. Now let's go through these headings because some of them will already been covered, like lack of communication, distraction, lack of resources, stress, complacency, lack of teamwork, lack of awareness, lack of knowledge, fatigue, lack of assertiveness and norms. Distraction's a real threat, particularly today with the use of devices and social media. Pressures to be expected when they're in a dynamic environment, when you've got to meet a deadline, and the ability of tasks may become too much. Learning assertive skills will allow a worker to stop and say, hey, no, and can communicate their concerns. So workplace practices, and all sort of workplaces, develop through time and depend a bit on that workplace culture. They can be good and bad, safe and unsafe. And they're often described, well, that's the way we do things around here, and they become norms. Unfortunately, they're not always appropriate. So in addition to the aviation sector, I thought of a few other human factors that might affect our performance. So different personality types affect our practice. Our outcomes different from high risk takers compared to the play it safe personalities. Is the engineer a team player or individualistic? And what's the role of ambition, hubris and arrogance, together with the more unsavoury aspects such as greed and avarice? Now, I didn't really know what hubris meant until I listened to the Lessons Learned session by Brian Leyland, where he attributed the role of hubris playing an important part in the failures of the Ruahihi and Whao hydro schemes. And if you haven't seen that, it's a very good webinar, and it's available on the Engineering New Zealand site. Our work environment can affect our performance. If we work in isolation, only considering one's own responsibility can lead to tunnel vision, a partial view, a lack of awareness of the effect of our actions and how they affect others. So it's important to ask others to check our work when we're gaining experience. Our Swiss cheese model has already been referred to today. Again, for those that are not familiar with it, imagine a series of slices with a bunch of holes in them. Some of those slices may be active, some may be latent causes, and when the holes line up, then we get an accident, mistake, or a failure. There have been a number of surveys on structural errors, and these indicate that 43% of the failures are related to design, 35% to construction, 15% to maintenance, and 7% for other causes. And of those for design, other research indicates that lack of knowledge accounts for 44%, motivation 35%, information 18%. So what about the costs of design errors? And the Australians carried out a survey on 139 construction projects, and there the design error costs were estimated to be 7% of the contract value, regardless of the contract type or procurement. So I've tried to have a look at what the GDP might be for the construction sector in New Zealand and had a look at some of their data, plus the data from the PricewaterhouseCoopers study for Engineering New Zealand. So maybe of the order of about 20 billion a year. So if we convert that, errors and mistakes in design could be costing, $1.5 billion a year, which is quite a tidy number. So structural engineering, uncertainties abound. Our task is to synthesise a solution which meets the client's requirements. Not only must it be designed to be safe, it must meet functional, performance and environmental requirements and be delivered at an acceptable cost. So uncertainties are a perpetual companion for us. Through design, we construct imaginary buildings with uncertain geometry, with materials of uncertain strength and quality, to withstand loads and environmental conditions of uncertain magnitude and kind. To that we must add the human factor, which means that there's an uncertain amount of errors and deviation from what was intended that will be incorporated in the final structure. Sometimes these are obscured to the practicing engineer by the development of design codes to manage some of the more important ones, for example, loads and materials properties. Engineering Modelling Uncertainties, EMU, was developed by Swedish researcher Frodeberg, who showed that well-defined engineering tasks generate a large variation when solved by different engineers. EMU has a large impact on structural safety. It is usually time-dependent and diminishes throughout the design process. So normally it's not possible to obtain a correct solution. It's usually a range of acceptable solutions is more appropriate. Other studies, Dehan and others, show that self-checking of designs, even just simple tasks as looking up tables, show an error rate of 2.4 to 3 times the chance of errors compared to those with independent checking. So again, that reinforces the need and the critical role of effective quality assurance and independent when checking. So in Sweden, 17 engineers of varying experience were given tasks, design tasks, and given limited time to carry out them. First was this 5-storey concrete building. Second was to design a truss over a stadium, a 68-metre span truss. Afterwards, they had a qualitative review. The results indicated a 300% range in the loads of the ground floor column of the 5-storey building, and the steel on the trusses varied between 20 and 50 tonnes. Also, an important finding of the review was that the majority of those 17 engineers had had little review of their calculations and their work and their practice up till that time. So what then makes a good workplace and a good engineer? I'd suggest it's a happy workplace where there's openness, good communications, a just culture that will provide satisfaction for all workers, enable them to reach their potential, improve productivity and reduce mistakes. Now, coming back to aviation, there's a YouTube video, Defence of Flying, which has some good points on human factors that also are relevant to us. These include the difference between attitude and values. Attitude can be short-term behaviour and easily manipulated, whereas values are long-term, developed over time, that include what means most as a backstop to decision-making and making the right choice. Empathy can be our greatest advantage in understanding others, but also our greatest weakness, especially if you do not want to disappoint. So understanding human nature, good self-reflection, a strong code of ethics and values help to make the right choices and become a good engineer. So I believe that better understanding of human factors, as in aviation, they'll lead to improved outputs. And if we can emulate the success the aviation industry has had by adopting human factors, maybe we can get the tenfold reduction in errors and accidents that we need. I believe that positive aspects will flourish and that our profession will be better off. Thank you.
Afternoon, everyone. As Hamish alluded to, we talked about this in the last conference in 2019. Sort of introduce some of the sort of observations and trends that we have seen in the sort of consenting sort of phase. I'd like to start off with, I guess, a couple of emails that I sort of got after the conference last time, and it sort of highlights, I guess, what was gained from it. I guess you can sort of see some of those sort of key topics that we've already covered off today, and sort of continue on today. Upping our game, awareness, and I guess momentum for change. Those are a few things that stick to mind. I guess at the same time, we're still seeing, I guess, some of the sort of examples of poor engineering, sort of confrontational nature, and that can be sort of seen as bullying, which sort of are the behaviours that we're sort of trying to sort of mitigate in our sort of careers. So I guess, are we getting better now? And I guess that's probably one of the questions that we'll sort of cover over this. Before I go for that, I think I just want to go through some of the procedural items that is sort of made up of your consent, and sort of bring a bit of context to what is actually done in a regulatory review. So I think most people are aware of what you sort of submit through your consent packages, your specifications, your calcs drawings, science features report, PS1, and after that, should there be any sort of questions that arise from that, RFIs that are generally generated. These are normally covering off missing documents, updating PS1 clarifications or conceptual checks. And once all those are sort of cleared off, consent is granted. So the councils sort of look to classify buildings in sort of three categories depending on the complexity. Your category ones are your sort of single-storey houses. These are normally screened out, so I guess the engineering sort of side doesn't get looked into. I guess our main focuses are on the sort of category 2 and category 3, and the category 3 ones are sort of more complex buildings, and they sort of are sort of brought about by sort of the soil conditions that you're in. They can be lead to semi basements in buildings. They could be lead to sort of the ECD wind zone that you're in. So there's a lot of things that sort of come into it. In terms of category 3 buildings, there's some that we don't necessarily look at, and those are sort of your high-rise sort of buildings, and they sort of normally have a sort of PS2 and sort of that sort of high rigor that is sort of beyond what we do as a regulatory review. These, I guess in sort of doing peer reviews, something to sort of be mindful of is that the person undertaking the peer review does have that sort of right experience, and you are sort of doing those sort of communication logs to see that, you know, the right questions are being asked. So in terms of the review time we get, you can see, so sort of for so Category 1 buildings, looking at sort of 60 minutes, and then for Category 3, we're looking at 3 hours. So I guess the role of the regulatory review is not, I guess it is just a screening tool. It's not, we're not looking through sort of all your sort of information. If you think about the work you sort of submit, your 100 drawings, your 200-page spec, and your 600-page calculations, we're not actually going to look at everything. It's probably more of a screening tool to make sure everything sort of ticks the boxes. And I guess this is sort of the actual times that we're looking at. So when you think about it, it is sort of in line with what is being expected. So this is, I guess, a slide that I put up in 2019. I still find it a bit hard to put up, just because I guess some of the comments that do get made to, I guess, reviewers can be quite confronting. And I guess the thing is, it is your responsibility as designers to sort of respond to RFIs in a respectful manner, if you might. It's not even a professional thing, it's probably more of a human thing. So I guess, let's all be nice to each other. What we're seeing in 2021, probably much the same. I guess there's still a lot of, trying to elaborate on things which are sort of unnecessary. And, when we even look at the question, do we actually need a response like that? I guess why would you waste your time writing that out when all you needed is a simple answer? So how should you respond to RFIs? I think just be professional, read and understand the question. Put yourself in the reviewer's shoes, I guess, and don't just go blaring out and just thinking you're right all the time. If it's an easy answer, then respond with enough information. If you think the answer is already in the documents, then just provide the right references to that. And if the RFI is valid and you change something, this is a good outcome. The system has worked, and change it, respond appropriately. I guess don't bluff your way through the answer. I guess this time and time again, I think we've sort of seen that, engineers will probably use their calculations and submit pieces of paper which probably don't have the information that you need. And I guess when this happens, sort of you go through multiple instances of RFIs, and then it's finally changed. And when people actually realise it's probably changing from, say, a M12 bolt to an M16 bolt, it's kind of a bit of nonsense. But it should just be done, to be honest. So we've already heard about this before, but this is probably one aspect that I probably want to discuss is around the modelling. When you can sort of consider the time that we get to spend reviewing consents, it's kind of hard to sort of make that judgment on the models and the models themselves. So I guess it's probably been covered earlier, but when I sort of thought when you should use modelling is really to understand and to validate your understanding of the behaviour of the model. I guess it's not the starting point to go to the model, and I think you have to really sort of, when we're sort of looking at sort of existing buildings, we really got to go through the drawings and sort of interrogate them and sort of have that basic understanding before we actually try and generate things. Yeah. Because I think what is actually happening to some extent is when modelling is pretty much used as the first point of call, and when the problem becomes too complex, i.e. we don't understand it, we don't know what we're doing, so let's just put it in the model and see what happens. And when that happens, what is happening is we tend to model every element, even though it's probably not necessary. Some examples, we're modelling sort of facade elements, we're modelling ground beams with multiple spring values, and these are causing those sort of 100 mode sort of models that we're still seeing. And that's the thing, we're not validating our answers. We're not checking that loads in equals loads out. We're not using those envelope sort of calculations and making sure that things are sort of working the way that we expect to. In many instances, we're just hoping for the best and saying that we've done an ETABS model and that's that. We're sort of taking the answers that we're getting and we're just rolling with them because that's what we think is right. And in some cases, we are using sort of inappropriate, we're using software inappropriately because we don't know what the right tool is.
Half time, you get me now to take over from Stan. Thanks, Stan. That's excellent. So in this talk last time, Stan went and gave some specific examples and put up some, some anonymised, I think, real examples. We're not going to do that this time. I think you're just going to have to take us our word for that, and there are plenty there. We were fighting over it for about 6 months, who had the best examples, Stan and I. So I don't think there's any real benefit in that. So what I wanted to do is just talk about perhaps some of the results of what we're seeing through our behaviours and submitting for consents, and also behaviours within the industry, and really where some of the councils are going with this. Here's a draft proposal that Wellington City Council is looking at around incidences of bad behaviour from engineers and what they have to do to manage that. And they are, putting a register down to see how they can manage that and how they can deal with this. Why do our consenting authorities, why do our clients have to do this? Aren't we professionals? Just a wee note, these are being shared around between councils, and councils are looking at, coming up with these processes. If you look at Auckland, they've got a different process where they pretty much make you go do a PS2 for everything, and the industry looks after it. But a lot of the regional councils and stuff, this is what we're getting. So let's just move on from that. What are we seeing outside the profession, or how are we seeing? This was from Paul Campbell's keynote of 2019, where he did a quick Google search on the engineer, and there was some pejorative instances of engineering there which weren't very hard to find. I thought, hey, this is a great slide. Paul, can I borrow that? And he said, yeah, sure, mate. I want to do the same. So I did some searches, and I also did some positive searches just to see what we'd get. And look, I'm going to start with the good, and hopefully this works. Yes, it is. Yes, we are getting some really good press, almost as much as the bad press now. So that, you know, Engineering New Zealand and others have putting out good information. You'll see here that we've got a lot more diversity starting to appear in the industry, and, you know, even Australians can be president of SESOC. We're seeing some awards. You know, we're seeing some of our good work recognised locally, and, you know, and people appreciate that, particularly when it relates to heritage or earthquake safety. We've seen engineers being the heroes. They've saved Auckland's traffic congestion. Well, they didn't really. They just put it back to normal. But anyway, some brilliant work by engineers, and just, you know, some amazing stories about how we came and saved the day. And, you know, so it makes me proud to be an engineer, to see some of the work like that's done and how we've come together. We've seen some international recognition. You know, SESOC Supreme Award winner last year, but also internationally recognised as, well, not last year, 2019, but internationally recognised. It rocks the world. Absolutely brilliant. Here's Alessandro, by the way, Hamish, so he's turned up. He's on the slide. He's been looking at ways to earthquake-proof bridges. And look, actually, it's good for us. We've got work coming, and we've got a lot of work in the future. We need apparently hundreds of engineers to deliver these government projects in the pipeline. So now's never a better time for us to actually, I guess, pull up our socks and really get on and show how great we are as a profession. And last but not least, you know, structural engineers saved the day. We managed to teach Jacinda how to make a proper birthday cake. We're recognised by the Prime Minister as very useful. The bad, I'm not going to dwell on that too much. You've probably seen all these. You've probably read all these articles. They are very similar to what Paul had on his slide in 2019, and they still keep happening. Hope, you know, they probably are a minority rather than a majority of what we do, a very small minority, but they are seen and noticed by the engineering community, and the public at large. You know, New Zealand Inc. sees that. And a couple of those bottom ones there, urgent industry change needed to combat poor construction. That's not just us, it's all the construction industry. But Structural Engineering Review finds system-wide problems and basic mistakes. These are big headlines. You know, if you saw them 20 years ago in the Dominion Post or the Herald, you'd be going, what? You know, we get a lot of information overload through electronic media, so we start to get a little bit, I guess, immune to seeing these things over and over again, but we shouldn't be. They're talking about us. What's the result? Well, we are seeing a little bit less tolerance from our clients. We are getting sued a little bit more than we perhaps have in the past, and people are expecting more from us. The public is less tolerant. We're starting to see our insurance position changing a bit, and it's getting hard to actually insure for certain types of work, and all of our premiums are going up. You know, all those who own a business will have noticed how much they've gone up over the last couple of years. You know, if we can't get insurance to do some of this consent checking work, who is going to check this work for us? That's not good for New Zealand. It's not good for anyone here. And lastly, you know, the regulator. Consultation has opened up on improving regulation of engineers. They've had to take notice and they've had to take action. You know, we currently have consultation on improving the regulation out now, and I read pretty much part one, and I get about down to the first paragraph after the bullet points, and this is pretty strong stuff. The public need to be protected from us through occupational regulation because we're negligent, reckless, or dishonest. Yeah, as being an engineer and loving the profession and putting a lot into it over the last nearly 30 years, I'm really disappointed to see that we've gone from a profession that was the most trusted professions to one that has to be strongly regulated. And anyway, to summarise, we are still seeing a few poor behaviours in submission. Similar to what we talked about in 2019, councils are now being more active in monitoring. There's less tolerance by the public for poor engineering outcomes. We are seeing a more active, litigation front, and the outcomes of affecting reputation and trust and the media coverage. It's so easy to put media coverage out there now. You don't have to fight for space on broadsheet media. It can just get out there. And Phil Pennington loves to find engineering stories from Radio New Zealand. And our regulator has been forced to act as a part of this pressure. So, now is the time to look at what we've got to and move forward and show that we're a great profession. Last but not least, this is just a house, but an engineer will have been here in some of these positions. How many of the things can you see here that perhaps are not the best engineering or could have been dealt with better? It's just a question. And that's the end of that talk. Thank you.
Okay, good afternoon, everyone. It's quite heartening to hear John talk earlier. It seems that we're going to touch on many of the same themes. Also good for him to acknowledge some level of plagiarism, it seems. Okay, so the talk I've been given is about computer modelling and the importance of knowing the limitations. More appropriate, really, though, is to understand the answer or the answer you're looking for before you even begin with the modelling. This was gone through at length by John, so I won't go too much into it, but there'll be a lot of the similar themes through this talk versus what John was alluding to. The key purpose when we start attempting a model, we've got to just determine what the purpose of it is. I've come up with three bins there for what we may be trying to do. Obviously, design being the mainstay for most of our work, through assessment, which gets a bit more difficult, and then forensic level investigations. To the left of that, design is typically linear and simple, and uses ratified and verified design codes and procedures, and have an inherent conservatism necessary for the task. At forensic level, we're more interested in basic mechanics of materials and fundamentals of load paths that may not be immediately obvious. Assessment in between all those is, of course, one of the more difficult ones, because you're trying to implement general design practices and principles and maintain some level of conservatism. They're reduced from design, but not necessarily looking at every piece of aggregate or reinforcing in the entire building. So we've introduced the idea of, and it's come up already, that you've got linear and non-linear analyses. Linear analyses are obviously the ones we do mostly, so I think it's important for us to define what the different analyses types are and when they would be mostly used. So for linear analyses, we split between static and dynamic type analyses. The routine ones being in this block. The key one there being earthquake actions are considered in each box we'll talk about today, but in varying degrees of complexity. Again, for non-linear, we've got similar processes, where we're looking at different effects such as construction sequencing or nonlinear behaviour of during earthquakes. Importantly, you'll note that there is no such thing as a nonlinear response spectrum. More importantly, we generally associate nonlinear behaviour with earthquakes. We all understand the concepts of ductility, plastic hinge rotations, pushover type analyses, and nonlinear time histories becoming more commonplace via the assessment guidelines. But it's also important to note that nonlinear behaviour exists in many other facets. We talk about things like material behaviour, stress strain level, or time dependence. Geometric nonlinearity in terms of second order effects, be they seismic related or at wind or gravity demands. We also talk about catenary cables, which have large displacement problems and therefore nonlinear, and construction sequencing, which locks in stresses that aren't necessarily apparent. So what I want to do is, I've got a couple of examples that we've come up with. They've been selected for several reasons. One is that they come up with reasonable regularity in our office in a support sense, but also they generally cater well to good pitches. The first one is one we would all know. It's tension-only brace frames. It's very obvious how they operate. I think everyone understands them fundamentally. But what the purpose of the slide, the purpose of the examples is to demonstrate how we often idealise inherent nonlinear behaviour as linear for analytical convenience. So then similarly, but more slightly abstract, is reinforced concrete walls. Reinforced concrete walls are inherently nonlinear even without ductility, just purely because of their the material behaviour of the concrete. Obviously, we accept this inherently. We routinely apply these stiffness reduction factors out of 3101, blindly, mostly. So on some level, we understand that the model cannot represent the underlying behaviour of the material. So let's look at our first example. Pretty boring stuff really, but it serves the purpose. So we've got a 10-storey brace frame with tension-only bracing. Now tension-only bracing obviously occurs for these slender elements because they buckle, which is geometric nonlinearity. Okay, so this should be pretty obvious, I think. Everyone would accept this already. That if we apply a set of consistent forces to both frames, where we're modelling one as linear and one as nonlinear, the nonlinear analysis deforms more than the linear process, which I think we all understand and accept, because obviously the linear one will have compression and tension acting at the same time. Obviously the difference in the behaviour is indicative of the linear process being inadequate to describe the problem at a stiffness level. So what's often done is to modify the area of the cross braces with a factor of a half. So the intent here is that the stiffness of each bay is correct, but internally obviously we've applied a bit of a fudge to it. By doing so, we end up with consistent deformations for the same load set. So on the one hand, we'd be happy, and we may even say, well, we could do a response spectrum with that even. So all good. What happens though, is at a global level, we're happy with the results. We know that the total shear through the frame's correct. We know that the deformations are appropriate. But what we don't know, or what we may also know, is that the internal actions within the frame are now distorted. We end up with, for the linear process, we end up with still compression and tension that hasn't changed as a result of that behaviour hasn't altered as a result of the the stiffness change we've made in a force-based process, whereas the nonlinear one correctly shows our tension elements in effect, and the compression one, the one is undergoing compression strain, being inactive. So we know that that this shows us the internal actions within the frame are poorly represented by this process. When we look at the ratio between the two, we can see that the ratio of the linear to non-linear brace forces is of course a factor of 0.5, which we I think understand and already know. What's not immediately apparent though is that the column forces are also skewed in a similar way, but asymptotic to 1 at the bottom for a tall frame. Worse is the reaction forces we get at the bottom of the frame. Obviously, the linear one presumes that we can still get half the reaction to each pile, whereas in fact the only pile with a reaction on it should be the one with the tension brace active. So again, the ratios of the forces between the two processes are quite marked. So the key thing here is that modifying the stiffness, which is a generally undertaken process, can have its benefits, but extreme care needs to be taken when interpreting the internal forces. The member forces are always going to be incorrect, and some level of judgment / post-processing, if possible, will be required. It's a very difficult task, and especially when you've got response spectrum, it can be near impossible, or if you've got brace bays of different widths and heights adjacent to each other. So what about the concrete wall? To many, the concrete wall seems doesn't appear to have the same shortcomings. In this concrete wall that I've made up, the key things are that we've got a uniformly distributed reinforcing spanning within the wall. We've got a large ground beam and a pile each end, and because it makes it easier, no axial load. Again, we want to model the two walls in two ways. One with linear membrane elements, which inherently have isotropic material behaviour, and then again with a sophisticated nonlinear layered shell to go to the other extreme. We're going to apply the same forces again. We're looking at the force domain here, and to see what happens. So the pair shear forces between the two models, there's a good check. We know that they should be the same, and they are. You might not be able to see the values, but it's good, they are. So, and similarly for the pair bending moments. So this shows that the way you model it does at a force level anyway. Obviously, you can still design these walls using the linear process. But what we're trying to show here is what the underlying behaviour and the non-linearity that's present is actually manifesting as. So let's look at the stresses. These are the vertical bending stresses in the wall. Again, we know this shouldn't be a surprise. We already know that we would generally use these values for design and use appropriate PM interaction curves and standard shear design formulas. We wouldn't be using stress fields for the design of a reinforced concrete wall, and for good reason. The linear model on the left shows that that the wall thinks is a neutral axis at the midpoint of the wall. The one on the right shows which is the yellow band. The one on the right shows correctly that the neutral axis migrates when bending as cracks form at the bottom of the wall and the reinforcement is mobilised. Again, this is not news, I would think, because we usually wouldn't be looking at this. So I think we all know it's there, and we wouldn't do that. The key thing is, though, what about the ground beam that we talked about that's modelled at the bottom of the wall? This is the output from the linear model showing ground beam deformations, shears and bending moments, and importantly the applied forces at the top. If we look at the similar one for the nonlinear wall, we can see that there's severe differences here. The nonlinear behaviour is correctly reflecting the internal stresses within the wall, whereas the linear one is not. The difference in magnitude is extreme. I'm not sure if you can see them, but the bending moment in the nonlinear one is 3,000 versus about 500 for the linear one. The deformed shape is a bit of a key giveaway in terms of why that is. And when we look at the free body forces acting on the beam, they are merely reflective of the stress field that is being generated at the bottom of the wall. So clearly the linear one is valid with the right assumptions and procedures in place. Because we'd said that because the bending moments were all good, we could have designed it. But what we need to be careful of is that the ground beam that's in the model is, we need to consider that as being in a similar vein to we would consider the internal stresses that are present in the wall itself. So what if we extend that to 3 piles? Again, nothing's changed upstairs, the bending moments and etc. are the same. But the pile forces are quite different. The linear one with the neutral axis of the midpoint of the wall thinks the middle pile has no demand, whereas the nonlinear one correctly allocates the tension to the middle pile as well as the outside pile. And importantly, it also importantly shows that the compression pile is increased in demand. The demand on the compression pile is increased due to the reduced lever arms. Now, this is all very interesting and good fun, of course, but it's not real. I'm certainly not advocating that this process would be something you do on a daily basis to determine the ground beam force. So it goes back to earlier comments that we've got to pick the right tool for the job and do the level of work that's warranted for the task at hand and use other methods. So in this instance, all we'd need to do is apply the stress that's at the bottom of the wall onto the beam. That would then give us the correct bending moment and pile force by hand. So what have we learned here is that for an inherently nonlinear system such as a wall, we can describe the global behaviour of it, be it at a stiffness level for stiffness reduction factors, or at a force level by integrating the stresses to form global bending moments and shear forces. Local stresses, again, they're not suitable for use in any process, unless it's of course a steel wall, but it's unlikely. And we need to treat the ground beam and piles as a sub-assembly of the wall itself, where the demands are derived external to the process, considering the reinforcing layout rather than the bending moments coming out of our software. The other thing to of course be mindful of is that the ground beam is also required to carry axial forces in a similar way as we saw for the cross-brace frame. In the cross-brace frame, if we want to mobilise the second pile, we have to drag that force back to the other pile. And a similar problem exists here, but would not manifest itself in the output from the model. So, what conclusions we got? The key thing here is that linear analysis procedures are generally adequate, and they have been around for some time, and that's why we do them all. They've been well verified and especially when used in conjunction with design procedures and codes, they are adequate for the purpose. We need to be very careful when determining local actions when underlying behaviour of the system is non-linear. The forces applied to the ground beam are a good example of why we always need to reconsider the effective free body diagram that reflects the underlying non-linear behaviour of the system, as though that's the real force that we need to design for. And of course, these examples are quite trivial in their complexity. Real-world scenarios, as I said, with multiple bay widths, heights, and analysis procedures make things a lot more difficult to determine what's going on, and certainly less intuitive. The key thing, it's not, I guess I can't just give you all problems, but the key thing here is that the easy workaround is to design with capacity design to keep these things at bay. Okay. I'd like to have a rant, so my 2 cents. Obviously, I'd like you to buy more black boxes, please, but it's helpful for me if you understand a few things as well. So the key thing is don't use the structural analysis program or a feature within it unless you fully understand the procedures and approximations that are used. The most important thing in my mind is to understand and define the loading, material properties and load paths, etc., before we begin a computer model. To me, the conditioning of the problem is the most important part. The computer modelling is a subset of the overall task we're all tasked with doing. Conditions, yep. So to me, the computer modelling is the easy part. The hard part in engineering, in my belief, is defining the inputs and interpreting the outputs. I'd say you could get almost anyone to build an ETABS model these days and get it to be sensible, if the inputs are conditioned properly and understood. If we've only got limited time, focusing on the inputs is more important than the model itself. And read the manual. Yes, that goes back to, I think, a similar thing that John was saying before, that I think a good mantra to live by is to do things as simple as possible, but no simpler than is necessary. We've obviously got a task at hand to do, and different levels of work, be it design, assessment or forensics, etc., will warrant more complexity in certain models, but we certainly don't need to. There's no point in chucking everything at it. We want to do the bare minimum to get the answer that's warranted. Thank you.
Thank you, Tony, and it was nice to finish with some real worked examples of some of the themes from the earlier conversation from John. Look, we've got a few minutes. If anyone's got any questions they want to ask one of our panellists, we covered quite a bit of territory there. So if there are a couple of questions, Peter.
Hello. Yep. I was just wondering, Stanley and Carl, just a question about building consents, etc., because I understood that about a year ago, Engineering New Zealand was looking at having a think tank on the peer review process, and I've heard no more. Did that ever happen? Because it was getting pretty ropey at the time, and all this infighting was going on, so I would like to see some more of that happen at a high level, so we start to talk to each other, a bit like marriage guidance. I'm quite good at that.
Oh yeah, this is working. There was no switch to turn it on. Well, you probably have to talk with Engineering New Zealand, but yes, I guess the whole peer review process is being discussed. A few years ago, there was an update to the guidance around that and practice notes. But yeah, more work has since been done since then. I guess they're pretty busy with occupational regulation at the moment and putting together submissions around that.
Could I just ask one more question? Do you think engineers and peer reviewers, for that matter, recognise the total dichotomy, the total difference between the design process on one hand and the assessment process of existing buildings on the other, where they are poles apart, and yet we seem to get those mixed up at times?
No. No, look, it does depend. By and large, I we do see a lot of very good work being done, by engineers on both design and assessment, as well as re-strengthening of buildings and using assessment procedures, combined with the building code verification, which is not easy. It's not a cookbook, but we also see a few examples occasionally, probably more than we'd like, but of where that hasn't been done so well, and you'll either see a design which has been designed clearly by someone who's done a lot of assessment and DSAs, or you'll see some assessment which doesn't necessarily follow the MB guidelines or normal assessment procedures. But those, I think, are the exception, but there are enough of them to be significant.
Seeing I've got the still, one more thing. Is that time for a small, more tuition training, whatever, because it's really bugging me?
I didn't catch that one, Peter.
Is it time for some more training from the industry about these differences and how to go?
Absolutely. There's always time for more training, and as you know, I've spent quite a few years trying to get training out there, as has everyone else on the SESOC committee, who over the 30 years of my career has put in a lot of time and effort. I don't know how many people there are to thank, but there are literally hundreds, and and SESOC will continue to keep doing that.
I mean, one thing I just wanted to say there, Peter, in response to your, I think it might have been your second question. I think, the new seismic assessment guidelines have done a great job at driving a lot more consistency in seismic assessment outcomes. So I think our industry deserves a lot of credit for the effort that's been put into developing those guidelines. We can always argue the precision or accuracy that were gained out of those, and neither of those things were perhaps ever intended. But I think the guidelines themselves have led to a whole lot more consistency in the outcomes that are being achieved, and a lot more grounds for engineers to be in agreement around assessment outcomes, which I think is a really good thing for the industry.
Yeah, thank you, Hamish. I probably wasn't clear enough on that. Yes, where people are using those guidelines, we are seeing a lot better outcomes and results. It's where they're not, or deviating from it, that's where we're not seeing the same consistency.
Very good. Any other questions? We've got one just here.
I guess it sounds like that a lot of the failures in design come from workplace culture, essentially. It seems pretty difficult to manage goodwill. Do you think there needs to be some sort of formal auditing or regulation of how workplaces are managed in terms of how they treat their employees and how they impart knowledge to them?
Sorry, I'm a little bit deaf and I didn't get the real gist of your question. My apologies. So someone rephrase it for me.
I will rephrase. Do you think that more onus needs to be put on companies to create a positive, empowering workplace culture that imparts the knowledge required to avoid mistakes? How do we regulate that?
I do. I think the whole issue has to be whole industry-wide. I think structural engineers, we can start the process, but I think it has to be adopted, as the aviation industry did, as an industry-wide initiative. I think individual firms and organisations can take the lead by doing that.
Yeah, I mean, just adding to that, if you look at health and safety and how we've come on in the last 20 years, and if we adopted a similar approach to learning and technical outcomes as we do to health and safety, you know, we would equally we wouldn't be having these discussions at all, I don't think. They'd be a rare discussion, much like the aviation industry.
Thank you. I think we've got another question in the middle, and we might call it quits there.
Thank you. Thank you. This one's to Stanley and Carl on the peer review thing once again. I wonder what your comments would be on the importance of the design features report in terms of interpretation by the peer reviewer. I think it's somewhere. It's the document which we could all work better. We put a lot of time into standards, clauses, codes, loads and what have you, and maybe not enough effort into the blurb. If you know what I mean by the blurb.
Yeah, I'd probably tend to agree. I guess the design features report is pretty important. It tells us, I guess, a good snapshot of what your inputs are, and I guess it's just start of your design, really. Yeah, it shouldn't be something that's filled out at the end. It should be something that's sort of done at the start and sort of followed through in your design. Can't stress the importance of it.